What would happen if a tire failed to withstand the moment of touchdown? In aviation, that answer is not allowed to exist.
So how must a tire be built to survive the impact of landing at over 150 miles per hour? Tia Storitz. Behind what appears to be a simple layer of black rubber lies a vast and complex industrial ecosystem. Continues through petrochemical complexes where polymers are derived from crude oil and moves into precision manufacturing lines for compounding, calendaring, and detailed assembly. In this video, we'll follow that entire process from raw materials and to the moment the finished tire leaves the curing mold and enters its final stage of inspection. The global aircraft tire market is estimated to be worth more than $2 to $3 billion per year. A figure that may seem modest compared to the automotive tire industry, yet it represents a segment defined by extremely high technical demands and formidable barriers to entry. Each tire is far more than a simple rubber product. It can cost several thousand to over $5,000, reflecting the expense of advanced materials, the engineering research, precision manufacturing, and rigorous certification requirements. Unlike passenger car tires that are mass-produced on rapid cycles, certain aircraft tire models can take 6 to 12 months to complete production and receive approval. That timeline includes extensive material testing, structural inspection, overspeed trials, overload testing, and long-term durability evaluation before the tire is cleared for operational service. It is this combination of high unit value, extended certification cycles, and uncompromising safety standards that makes the aircraft tire industry relatively small in volume, yet strategically significant within the global aviation supply chain. The journey of an aircraft tire does not begin inside a factory, but among rubber trees growing in the hot, humid climate of the tropics. A thin, carefully controlled incision is made through the outer bark, allowing milky white latex to flow slowly into small collection cups attached to the trunk. On average, a mature rubber tree yields only a few dozen grams per day, roughly 1 to 2 ounces, a modest output compared to the volume of material ultimately required by the aviation industry. Yet that very sap will form the foundation of a structure designed to withstand operating pressures that can exceed 200 pounds per square inch in real-world service conditions. In your opinion, how many rubber trees are needed to produce the material for a single aircraft tire? Once collected, the latex is stabilized with a preservative solution to prevent premature coagulation during transport. At the processing facility, it is concentrated, pressed into sheets, and dried to form. Natural rubber with high tensile strength and strong elastic recovery after deformation. That's a critical property when a tire must absorb massive impact forces at the instant of touchdown. Alongside this natural source, synthetic materials are produced in petrochemical complexes through the polymerization of molecules such as butadiene or styrene.
This reaction forms long, stable polymer chains that allow the rubber to maintain elasticity across
Continuously fluctuating temperatures. The combination of natural and synthetic materials creates a compound flexible enough to deform under load, yet durable enough to perform under the demanding conditions of aviation operations. The black color of an aircraft tire is not the natural color of rubber.
In its raw form, rubber has an off-white appearance and is relatively soft,
And lacking the strength needed to withstand heavy loads or maintain structural integrity under demanding operating conditions. For that reason, the formulation used in aircraft tires differs significantly from that of passenger car tires right from the compounding stage. In this blend, natural rubber typically accounts for approximately 70 to 90% of the base rubber content, noticeably higher than in many passenger vehicle tires, which rely more heavily on synthetic rubber to optimize cost and tread life.
acting as a reinforcing filler that improves durability and resistance to surface cracking. While this proportion may be similar to
or slightly higher than that found in some automotive tires, aircraft tires require far stricter dispersion control
to prevent structural inconsistencies. Process oils generally make up only about 5 to 10% and lower than in many car tire formulations, ensuring the compound remains stable and does not become excessively soft under high loads. Once all components enter the internal mixer, high-speed rotating blades generate intense shear forces, allowing the carbon black and additives to distribute uniformly throughout the polymer network. At this very stage, the material distinction between an aircraft tire
and a conventional road tire is firmly established.
Once the rubber compound reaches the required level of uniformity, the production line moves into the stage of forming the reinforcement plies. The reinforcing fibers, typically high-strength nylon or aramid, are woven into technical fabric sheets with a dense thread count. These fibers possess an exceptionally high tensile strength relative to their weight, and they are responsible for distributing loads when the tire is subjected to compression. Before being used, the cord fabrics pass through a rubber coating system, where heated rubber is pressed deeply into each fiber to ensure complete bonding. Unlike many modern automobile tires that use a radial structure with steel belts positioned beneath the tread, aircraft tires commonly rely on a bias ply construction. This means the plies are laid at opposing angles and stacked in multiple layers, creating a rigid and uniform carcass structure. At the same time the plies are prepared, the bead assembly is manufactured separately. The bead is not just a single steel wire, but a bundle of high-tensile steel wires wound in multiple turns under precise tension. These wire loops are then compressed into a concentric unit and encased in rubber to enhance adhesion to the tire body. The bead serves as the anchoring interface between the tire and the wheel rim, which is why dimensional tolerances are tightly controlled. Once the plies and bead assemblies are completed, the structural skeleton of the tire has effectively been formed. Once the plies and bead assemblies have been prepared separately, all components move to the forming area, the core of the aircraft tire assembly stage. Here, a specialized tire building machine, equipped with an expandable metal drum, is responsible for uniting each layer into a single structure. Unlike passenger car tire lines that prioritize speed, this system focuses on structural stability
and uniformity at every step. The process begins with applying the inner liner onto the drum surface.
This layer serves as the airtight foundation for the reinforcing plies that follow. Next, the nylon or aramid plies are laid in a bias ply configuration, depending on the tire's size and load requirements. An aircraft tire may contain between 12 to 20 plies stacked together.
Each layer is positioned at a calculated angle to distribute forces evenly around the circumference, forming a rigid and stable carcass capable of withstanding heavy compression.
The bead assemblies are then installed at both edges using a mechanical positioning system. These steel bead bundles anchor the tire securely to the two-piece aircraft wheel, making precise placement critical during installation. Once the beads are fixed in place, the sidewall rubber and tread components are added to complete the initial flat structure. After all materials are positioned correctly, the building drum expands. An internal rubber bladder presses the structure outward, transforming it from a flat layout into a uniform cylindrical shape.
The stacked plies now conform tightly to the intended geometry.
The completed green tire can weigh between 100 to 300 pounds, depending on its size and application. At this stage, the load-bearing framework is clearly established, even though the rubber has not yet been cured. The once separate layers have become a unified structure, ready to enter the curing mold, where its mechanical properties will be permanently set. Once the green tire leaves the building drum, its structure is still soft and mechanically unstable. The plies, bead assemblies, and rubber layers are held together primarily by temporary mechanical pressure. To transform this layered assembly into a true load-bearing structure, It must undergo vulcanization inside a heavy steel curing mold.
The green tire is placed into a two-piece heated mold powered by steam or high-capacity electric heating systems.
When the mold closes, an internal elastic curing bladder is inflated, pressing the tire outward against the mold surface.
That metal surface carries the full tread design, including the grooves and heat dissipation channels.
The mold temperature is typically maintained between 320 and 350 degrees Fahrenheit, high enough to trigger the chemical reaction,
without compromising the reinforcing fibers embedded inside. The curing cycle can last anywhere from 30 to 60 minutes,
depending on tire size and carcass thickness, which are substantially greater than those of most passenger car tires. During this period, sulfur forms crosslinks between the polymer chains, creating a stable molecular network. These crosslinks permanently lock the rubber into its elastic state, enabling the tire to retain its shape under heavy loads and the intense heat generated during landing.
Once the cycle is complete, the mold opens, and the tire undergoes controlled cooling.
At this stage, the tread pattern is fully formed, and the internal structure has transitioned from a pliable assembly into a stabilized load-bearing system.
It is here that the mechanical integrity of the aircraft tire is fundamentally established,
before moving on to rigorous inspection procedures. Once the aircraft tire leaves the curing mold,
it does not go directly into storage. Instead, it moves through a series of rigorous inspection procedures. The process begins with visual inspection, combined with dimensional measurement. Laser measurement systems and precision mechanical gauges are used to verify overall diameter, section width, and concentricity relative to a calibrated axis. Next comes pressure and air tightness testing. The tire is mounted onto a test wheel assembly and inflated under controlled conditions to evaluate its ability to retain pressure over a specified period.
A critical step follows: X-ray inspection. This technology allows technicians to examine the internal ply,
structure, bead positioning, and material distribution without cutting the tire open.
For selected production batches, functional testing may also be conducted, including high-speed rotation or load simulation,
under controlled conditions to confirm compliance with aviation performance standards. Only after successfully passing this entire inspection sequence
is the tire certified and cleared for operational service.
After passing the entire inspection process, the tire is not placed into service immediately.
The next stage involves mounting it onto the wheel assembly. Aircraft wheels are typically designed as two-piece assemblies, allowing high-pressure tires to be installed and removed safely. Before installation, both the tire and the wheel halves are carefully inspected at the contact surfaces to ensure there are no foreign objects, scratches, or deformations that could compromise the airtight seal. The tire is positioned onto the lower wheel half, and the upper half is then aligned and secured. Using specialized bolts tightened to specified torque values. At this stage, the bead plays a critical role, as it must seat firmly into the wheel groove to create a secure mechanical interface. Any misalignment during wheel assembly can lead to imbalance. Instead of ordinary compressed air, the aviation industry uses dry, pure nitrogen. The reason lies in its stability. Nitrogen expands less with temperature fluctuations and contains no moisture, reducing the risk of internal oxidation within the tire. Eliminating oxygen also lowers the potential for combustion in situations where brakes generate significant heat during landing.
After reaching the required level, the wheel assembly is observed to confirm there is no pressure loss.
Before leaving the maintenance facility, the wheel is also dynamically balanced to minimize vibration during rotation. Only after completing installation, nitrogen inflation, and balancing is the aircraft tire considered ready to be mounted onto the landing gear and enter operational service.
From droplets of latex deep in tropical forests to heated steel molds inside industrial curing presses, from cross-laid reinforcement plies to steel bead bundles, locked into a two-piece wheel.
The journey of an aircraft tire is a sequence of tightly controlled processes. On the outside, it may appear to be nothing more than a black rubber ring.
Rolling along a runway. Yet inside, it is a multi-layered structure engineered to withstand immense loads
And brake-generated heat and repeated high-impact landings over hundreds of operating cycles. Every material layer, every vulcanization reaction,
and every X-ray inspection contributes to a level of reliability that aviation simply cannot compromise.
If you found this journey worth exploring, make sure to hit like to support the video. Let us know in the comments.
Which stage of the aircraft tire manufacturing process impressed you the most? And don't forget to subscribe to the channel so you won't miss the next episode, and
where we continue uncovering the industrial systems operating quietly behind the modern world.